Have you ever tried to measure something so small it's basically invisible? I mean, think about a single layer of paint. Now imagine something a million times thinner than that, thinner even than a single atom. How in the world would you measure it? Well, today we're diving into the pretty amazing science of how we do exactly that. So this is the big question, right? How do you measure something that you're building literally one atom at a time? You can't use a ruler. You can't even really use a microscope in real time. It seems like it can't be done, but the solution is surprisingly brilliant.
To get our heads around this, we first have to appreciate the scale we're talking about. This is the nano world, where all the normal rules of measurement just go right out the window. And the hero of this whole story, the thing that lets us see into this invisible world, is a material you've definitely heard of: quartz. Yep, the very same crystal that keeps time in your watch is used for something even more precise here.
So what's so special about quartz? What's its secret? Well, it all comes down to a constant, incredibly stable vibration. Like a hum that's so predictable we can actually use it as a ruler for the atomic world. Now, this magic has a real scientific name. It's called the piezoelectric effect. And it's a two-way street. If you squeeze a quartz crystal, it creates a little electric charge. But, and this is the important part for us, if you apply electricity to it, it vibrates with almost perfect consistency. That vibration, that's everything.
Okay, so how do we use that vibration? Think about it like a perfectly tuned bell. It rings with a very specific, pure musical note, right? Now, what happens if you add just a tiny speck of dust or a drop of paint to that bell? The tone changes. The pitch drops just a little. The quartz crystal works in exactly the same way.
And when I say it vibrates, I mean it really vibrates. We're talking about the crystal's natural resonant frequency, its sweet spot, which is about 6 megahertz. That's 6 million vibrations every single second. It's this incredibly fast and stable hum that turns the crystal into a hypersensitive scale.
So, we've got our core idea, a vibrating crystal that changes its tune when you add mass to it. Now let's see how that's actually put to work in a real-world system.
And here it is, the whole setup. This all happens inside a vacuum chamber. You've got your source material over here being vaporized, then you have your target, the thing you're actually coating, and right next to it, you've got our little quartz crystal sensor, placed so it gets coated with the exact same material. So what gets the whole process started? That would be the oscillator. It sits outside the chamber, and you can think of it like the conductor of an orchestra. It sends a steady electrical signal to the crystal, getting it to vibrate at that perfect 6 megahertz frequency. And here it is. This is the crucial moment. As that vaporized material settles onto the target, it's also settling onto our quartz crystal. And even though this layer is impossibly thin, it has mass. And just like the paint on our bell, that tiny bit of extra weight slows the crystal's vibration down. The frequency drops, and that drop is exactly what the system is listening for.
So, listening in on all this is the monitor. Its job is pretty simple, but it has to be incredibly precise. It's basically a frequency counter. It is constantly tracking the crystal's hum, second by second, and the instant it detects that tiny drop in frequency, it knows mass has just been added.
So the system measures a change in frequency, a change in hertz. But that's not the same as thickness, right? How do we get from a change in a hum to a precise measurement in nanometers? It's time to decode the data. The monitor sends all that frequency data over to a microprocessor, which acts like a translator. It crunches the numbers and answers 3 really critical questions for the engineers. 1, how fast is this layer growing? 2, how thick is it right now? And 3, how much longer can this crystal keep measuring accurately before we need to swap it out? It gives them total control.
So you see the measurements are in angstroms. Just how small is an angstrom? This is where it gets absolutely wild. To give you some perspective, a single hydrogen atom, the smallest atom there is about half an angstrom thick. This system isn't just measuring thin films, it's measuring the buildup of material, 1 atomic layer at a time, in real time. It's just incredible.
Okay, so the technology is obviously amazing, but this isn't just some cool science experiment. Why does this level of atomic scale precision actually matter in our everyday lives?
Well, it turns out this precision is the hidden engine behind so much of our modern world. The computer chip in your phone, the anti-glare coating on your glasses, the super specialized mirrors inside space telescopes, none of that stuff would be possible if we couldn't build and measure these perfect ultra-thin layers.
And that really leaves us with a fascinating final thought. We've figured out how to measure matter 1 atomic layer at a time. As we get even better and more precise at this,
What new technologies is that going to unlock? What are we going to be able to build when we have perfect control over the fundamental building blocks of the universe?